Okay, so today what we're going to be talking about here in this video is the sinusoidal source. Up until this point, our voltage slash current supplies, let's see here, current supplies have been DC. So sinusoidal sources are our first example of an AC signal. Now, the name is a little deceptive when you see sinusoidal source. Sinusoidal refers to either sine x or cosine x. And in fact, cosine x is going to be the more common one we encounter. And so let's give an example of what we mean by a sinusoidal source and then talk about some of the important parameters in here. So let's just for arguments start with saying we have a voltage source. And so we're going to say V is equal to V sub m. And then, as I said, we're going to have cosine typically here. And then we have omega t plus phi. Now, there are some very important things here. Vm, and this is stuff we should just remember from trig. Vm, of course, is what we call my amplitude. And the reason we have sub m, you can kind of think of this as also, the reason they do that is they think of it's the magnitude. And so you can think of it, if it's got no DC offset, it's of course the highest peak that the sinusoid source would get. And then we can also think of omega here is what we refer to as the angular frequency. Which is, units of this would be in radians per second. And of course, I should put here maybe that when we're talking about this, of course, the units for this would be volts. I mean, it's a voltage. And then we also have the period, which we can talk about. And period, if we just again go back to trig, you can get that the period is 2 pi over omega. And then the units of this would be in seconds. And then we can also talk about f, which is the frequency, which the unit's frequency is in hertz, which is actually equal to 1 over second, which is sometimes written as second to the minus 1. So that's the units for hertz. And of course, this is, again, as I said, this is 1 over t. Or you can think of this as, if you go back to the equation for the period, you can think of this as omega divided by 2 pi. And so in some textbooks, you will also see this written slightly different. You'll see sometimes that they write this, in fact, as V equals Vm cosine of 2 pi times f times t plus phi, and in volts, because they want to just isolate what the frequency is in hertz in the equation here. So we're typically going to write this as omega t, but it's important to recognize omega and f, because in some of the problems that we will be examining this semester, sometimes we'll be given what omega is, and sometimes we'll be given what f is. No matter which one we're given, we can easily compute the other. If you're given f, to get omega, you multiply it by 2 pi. If you have omega and you want to get f, you do 2 pi divided, you do omega divided by 2 pi. So very easy to manipulate all through them here. Now there are two other things that are very helpful for us in these problems, and one of them is these are going to be cofunction identities. I'd like to go back to the black here. Cofunction identities. And for instance, if we were looking at what the sine of x is. Now, when we said a sinusoidal, we said we're going to mostly use cosine. In fact, not only are we going to mostly use cosine, with the analysis we're going to be doing in this course, we're always going to want our voltages to be a function of cosine. We're never going to want to use the sine function. But we can easily write this in the terms of cosine, because the cosine co-identity here is that this is equal to x minus pi over 2, or if you're using degrees for that phase angle, it would be x minus 90 degrees. So, and if you think about this for a second, that shouldn't be too surprising for us. Think of the graphs of cosine and sine. So let's just look at the graphs here. I'm going to just real quickly sketch cosine and sine, and then put some axes in here. So I'm not even doing a very accurate sketch of these. But we can see, of course, the cosine function, this would be cosine, starts at 1 and then goes down and then up, and then the sine function just simply starts at 0 and then goes up and down. But we can see clearly if we just moved, for instance, I'll draw this little piece here. If I just moved this cosine function a little bit to the right, I would have the sine function. And well, minus 90 degrees or minus pi over 2 is a horizontal shift to the right, so I literally am just moving this cosine function a little bit to the right, which gives me the sine function. Because as I said, we know that sine and cosine are essentially the same, they just start at different locations. So we can always write the sine function in terms of cosine. So this is a very critical identity that we're going to want to use. Now there is another one. I'll just go ahead and write it down for completeness sake, but we're not really going to use this one. You can also say that cosine of x is equal to the sine of x. Well, actually I have to be careful. It wouldn't be this one. Let me be careful here. This would be, I believe it's pi over 2 minus x is what we would have. So as I said, we're not going to really use this one. I want to be careful to write it. Technically, if you look up what the cofunction identity for the sine function is, they actually say it's cosine of pi over 2 minus x. But since cosine's an even function, we can actually put it in any order, and this is the order we're going to want to use it in this course. So that's why we write it like that. Now, as I said, this second one, it's important for completeness sake, but we're not going to really use it. All right, so let's do a real quick, easy example here. So let's look at an example of v equals 10 cosine of let's just say, in this case, 500 pi t volts, and then we're going to determine what Vm is, we're going to determine what omega is, we're going to determine what the frequency is, we're going to determine the period, and we're going to determine phi. And so, again, a lot of this is just easy looking at by inspection. Vm is easy. We can just say, oh, look, it's right there. It's just 10. And then we can also see here, well, what omega is. It's just simply the number in front of t, so that's 500 pi. And then f, remember, is omega divided by 2 pi. Which would be 500 divided by 2 pi, which of course is just 250. And I forgot to put units on these. VM, we don't actually put units on typically unless it's micro or something. We don't write volts or anything like that necessarily on it. But this is rads per second, and this would be hertz. And then the period, well, that's 1 over 500 pi. I'm sorry, I'm doing it completely wrong here. Got myself a little mixed up here. This would be 2 pi over 500 pi. Or remember, once you have the frequency, you can just do 1 over 250. And I don't have this computed out here, so let me pull up my handy dandy calculator and do it real quickly. And this would be, and we want to use engineering notation, so this would be 4 milliseconds. And then phi in this case is 0 degrees. And we often write phi in degrees. You can also do it in radians, but it's 0 degrees because there is no angle there. One other quick example here. And the other quick example would be, I'll do this time a current equals 3 sine of 10t milliamps. And so in this case, we don't have a VM to compute, but we're going to compute all the same things. We have an IM. So we're going to compute all of these things here. But before we do this, remember, all these definitions we had, this phi here was assuming that we had it written as a cosine function. So we need to first convert this sine function. It's the most common mistake I see people making all the time. You need to convert this to a cosine function. So this would be 3 cosine of 10t minus 90 degrees milliamps. Now we can go ahead and compute everything. Well, I'll go ahead and put units on this, even though, as I said, it's not necessary to always put units, but I definitely want to make sure to capture the milli. So I'll go ahead and just write 3 milliamps down for IM, because you want to make sure to capture 3. I mean, technically, I guess you could write this as 0.003, but we prefer engineering notation. Omega in this time is simply just 10 radians per second. And then the frequency would be 10 divided by 2 pi, which of course is not going to be a very pretty number. Rounding it to 3 decimal places, I get 1.592, and this would be hertz. And then, of course, we can get the period by doing 1 over the frequency, which is simply just by, now that I have this in my calculator, if I simply just do the reciprocal of that, I get, rounding it to 3 decimal places, I get 0.628, and this would be in seconds. And then phi, again, we can write it as either degrees or as radians, but we typically honestly write it as degrees, but we have to be careful. The sign always goes with it, so the phi here would be negative 90 degrees. So this angle phi is going to come into a very important role as we move on in our circuit analysis. Okay, so actually that's all we're going to talk about in this video. So again, this video is introducing the sinusoidal source. This is going to be the voltage source that we're going to use on all of our circuits for the first half of the semester. So we're always going to be looking at that the power supply is always a cosine function. As I said, it could be a sine function, but then we convert it to a cosine function, and that's going to be what we're going to be analyzing for the entire first half of the semester.